So for this last leg of our symposium, it's my pleasure to welcome Vimal Buck and his team. And they're going to be talking about using blockchain technology to help secure America's defense critical infrastructure.
Yeah, so I changed, but not just for this, for the last hour, but I'm going to talk a little bit about what this project was and give a little bit of overview of CDME, but these are slides that we were fortunate enough to go to NSA and present on to US Cyber Command, to all of US Cyber Command and a classified briefing, even though none of us were cleared. So this was a unique opportunity. The students, we all got to go and participate in this. And we did this as part of ICDT, the Cyber RECon competition. So Julia helped facilitate this. This is the team of students that worked on it. Aaron, Bryn, and Joe graduated and flew to Europe, so they were unable to even accept the award today, but I think Joe called in. Jacob and Shrika are here. And then that's myself and Major Julian Petty, who was our advisor from the US Army. So we did go to NSA headquarters and we were able to get a picture taken within NSA, so they had to bring in a special camera, but so you can kind of see most of the student team, Julia, Major General Osman from the Five Eyes Intelligence Service from Canada. So he was, Canada and Australia were the two that were kind of rotating through. So he was there over the summer. And so we were able to get that done. So I'm going to give a little bit of an overview of what CDME is in case you guys aren't aware. Some of you are very much aware, like Ted, who has probably seen this like 55 times. But in case you're not aware, we are an applied engineering research center on Ohio State's West Campus. We try to emulate a manufacturing environment. We have about 100 to 150 undergraduate students that are paid employees that work at the center. They're aided by about 30 or so research staff, such as myself. We have about 250 affiliated faculty and graduate students that also kind of assist out in different ways on different projects. Some of you in the room have been involved with those. And we operate on about roughly 50,000 square feet of ITAR and HIPAA compliant spaces on OSU's campus. Again, we work with companies of all sizes and projects. We do a lot of SBIRs and STTRs, and we sort of are a streamlined point of access for contracts and other things for businesses to engage with the university. Again, there are 7 different divisions within CDME. There's a very robust additive manufacturing division that has a lot of different 3D printing capabilities, a lot of different modalities of 3D printing, metal 3D printing, polymer 3D printing. We even had a concrete printer for a while. We've got an AI manufacturing systems lab that uses vision systems and a lot of Yaskawa robots and even autonomous robots, looking at how AI technology can integrate with robotics. Got a robust medical modeling materials manufacturing group that has space in the James Cancer Hospital and at Pelotonia Research Center. And then the industrial cybersecurity group that I run, materials and process group that operates a foundry, program management group, and then general lab services where people can come and do machining, 3D printing, water jetting, other things. All of this is driven by our undergraduate students who are the engine of this. They get the full experience of working on multidisciplinary teams. They do the soft skills such as project planning. They look at supply chain logistics, where to order parts. Everything is designed for manufacturability. And they learn personal skills going and presenting and doing in front of a lot of different both commercial customers and then also government contractors. Again, kind of more action shots here. You can kind of see the foundry in action. It's one of the largest foundries on a university campus. Ohio State has it. And it operates here. You see the bottom picture is just metal 3D printers. And you see some of the robotics. And then our group can do like PCB layout design, embedded systems. A sweet spot for our lab is sort of rapid prototyping, getting data from a sensor, sending it somewhere. We can do embedded systems, FPGAs in our lab. A couple of research projects that led to this one sort of being funded. We are part of the Manufacturing Times Digital Consortium. There's a lot of different Ohio schools that are part of that. We did 2 big projects for them. One of them was done with Ted and Carter, where we were looking at designing playbooks for small, medium manufacturers. So this was distilling a lot of NIST and MITRE standards and making it into like a TurboTax-like tool that small and medium businesses could use. We have the potential for some follow-up work in a slightly related vein with MXC on that, so they really like this project. And then we did one with Porsche, which is another company that Ted and I were working on. So looking at the blockchain in manufacturing, so we were able to demonstrate a demonstration in a facility such as CDME and then design a playbook for small, medium manufacturers. Jacob worked on that project. He's actually going to be interning at Corsair over the summer as well. But we delivered a playbook that shows, what are the challenges in small underutilized spaces for implementing blockchain technology. And then as Ted mentioned, we do have an NSF follow-up project with them where we're looking at trimming the blockchain and looking at like how to make it more efficient for deploying in like small under resourced areas. So then that led to, we've got this wide range of experience along blockchain. So for Cyber RECon, they were looking at personas and looking at, how do you figure out what a threat actor might be or who a threat actor might be using blockchains. And so we were able to kind of put together different parts and pieces of what we've been working on and then look at it through the lens of how do you secure defense critical infrastructure. So, and this caught the attention of NSA for a myriad of reasons, right? One of the things that they told us when we were down there was that when the hurricane hit, the water treatment facilities in Georgia were down. And then that took down this cooling systems for the supercomputing capability that NSA Georgia had. So their entire infrastructure shut down just because the water utilities there shut down. So then you kind of see how public infrastructure is very critical for defense, right? There's some on-site capability usually, but not enough where you can run everything all the time. So now I'm going to turn it over to these guys. They're getting pretty good at presenting this, so I can.
All right, so our problem was that critical water infrastructure is facing increasing cybersecurity threats, and we identified 2 attacks against Ohio water systems in the past couple of years. And as Vimal mentioned, the public water systems are vital for the defense, the whole DoD as a whole, and also civilian life. So a little introduction to public water infrastructure. There's 152,000 water and wastewater treatment systems in the US. Around 4,000 of these are in Ohio, and 80% of the US population relies on these treatment facilities. Most of these facilities have pretty aging infrastructure and also outdated systems. And there's also insufficient cybersecurity funding or resources for a lot of these facilities. So we wanted to find a way to help these facilities become more secure against cyber attacks from both nation state actors and just other threats. So to start our research off, we had a few subject matter expert interviews. First, we talked with Kirk Harith, who's Ohio's cybersecurity strategic advisor. We focused on understanding the state of Ohio water treatment plants and the potential risks that are associated with them, as well as past attacks against them. Our next major interview was with Lieutenant Colonel Danny Zhu, who is the AI task force lead for the US Cyber Command. We focused on talking about threats to water systems, as well as upcoming threats like AI and quantum computing. And then finally, we talked with Ben Scott, who's an Ohio cyber reservist that's overseeing their water infrastructure group. And we focused on the current system architecture and technology within these water treatment facilities. So a few current threats that we identified in our research were nation-state sponsored actors, advanced persistent threats, the waterfall cascade attack scenario, which is like what Vimal mentioned earlier, how civilian infrastructure affects the military bases, and then also critical infrastructure as an entry point to larger campaigns. So one of our main focuses in our research was the Typhoon groups. So Volt Typhoon is a group that's infiltrated various critical infrastructure targets across the US, and it uses IT networks to move to OT assets. And then also Salt Typhoon and Flax Typhoon. Flax Typhoon is a little more influential here as it hacks IoT devices, which are very common in these water facilities. So our base of our research is blockchain. So just a little overview for anyone who doesn't know about blockchain. It's a distributed immutable ledger technology. Cryptographic hash functions ensure data integrity in each block. It has a tamper evident design, and there's smart contracts that can automate security protocols or really run most programs. And then some of the main properties are traceability, enhanced security, and transparency. So in our research, we also looked at permissioned versus permissionless blockchains. We identified permissioned blockchains as the ideal candidate for our application, as there's known and vetted participants, and there's also greater access control and privacy. Some of these that we looked at were Hyperledger Fabric and R3's Corda. So I'm going to pass it over to Shrieker to go through our implementation.
Yeah, so thanks, Jacob. And so we've just covered like some fundamentals of blockchain and the key differences between permission and like permissionless systems. So now we can shift our focus to how we can analyze these behaviors on blockchain. And specifically, we'll look at how behavioral personas can be applied to security and threat detection. So in cognitive systems engineering, personas are usually used to model system behavior, user behavior to improve system design and usability. However, in the context of blockchain, you can use personas differently and specifically to categorize threat actors rather than just system users. And blockchain's immutability allows us to track and analyze historical changes. So that means that every action leaves behind breadcrumbs or small clues that, when you analyze over time, can reveal distinct behavioral patterns. And by studying these breadcrumbs, we can fingerprint specific attackers. These fingerprints are essentially unique patterns of activity left behind a given threat actor. And by leveraging this concept, we can start constructing behavioral personas for these attackers, identifying key patterns, strategies, targets, and methods of exploitation. So to take this concept further, we take an approach involving unsupervised and supervised machine learning techniques. And the unsupervised part, the idea is to cluster similar attack patterns together to identify recurring threat entities like the Typhoon attack series. By categorizing these fingerprints, we can start to develop some personas. And to break this attack fingerprint down, it can be formalized as what you can see up there with B1 through Bn representing a breadcrumb, which such as like in water infrastructure, you have things like flow rate or like chemical dosing. And these breadcrumbs are captured over time. So it's essentially time series data, and C represents other system state variables. Yeah, next slide. So this is the part that I mainly worked on, which is the machine learning framework. So our proposed framework is like specifically designed to process these breadcrumbs and extract actionable intelligence on threat actors. And at the core of the approach are two complementary techniques, as I mentioned before, supervised and unsupervised learning. The supervised being the variational autoencoder, which attempts to learn what normal operation looks like. And first, a high-level overview is that it has an encoder and decoder, and the encoder compresses the fingerprints into a latent space, which is essentially a smaller mathematical representation of the normal behavior, which it will be trained on. So when sequences deviate from established patterns learned by the autoencoder, so only trained on the normal data, if anomalous data is fed into the model, then it doesn't know what that looks like, so it'll have high reconstruction errors. So this is valuable for detecting sophisticated adversaries, like Jacob mentioned before, Volt Typhoon, who use living off the land techniques that traditional signature-based detection systems generally miss. And the second and parallel component is DB-scan, or density-based spatial clustering applications, which attempts to discover groupings based on data density. And this is crucial because we don't know in advance how many distinct attack patterns might exist in our data. Like if you look at Volt Typhoon, like you can't train on data from Volt Typhoon because you don't have that data available to you for attacks that you don't know about. So that was the body of the pipeline, and the ensemble anomaly score kind of takes a weighted sum of the reconstruction error from the autoencoder and the distance to the nearest cluster from the DB scan algorithm. You can go to the next slide. So here's some high-level implementation points. So first, we propose a SCADA system integration that would create blockchain-secured breadcrumbs for every command affecting critical processes. So operational data can't be deleted or modified by attackers. Second, we would implement administrative access tracking with cryptographic verification, which would create an immutable audit trail of actions taken during privileged sessions. Third, our plan includes establishing behavior facility-specific facility-specific behavioral baselines. Through initial monitoring, our system would learn normal operation, as I mentioned, like with the autoencoder, unique to each water treatment plant. Fourth, we'd establish cross-facility intelligence sharing. So when anomalous patterns are detected at one facility, they can be securely shared with others without exposing sensitive data. Finally, we'd integrate P2RP, or persona preserving reputation protocol, in our regulatory compliance reporting, which would use dynamic reputation scores for data sources, ensuring only verified entities with proven reliability influence security assessments. And this proposed architecture is designed to address resource constraints in water treatment facilities, specifically smaller ones that lack dedicated cybersecurity teams, but remain critical infrastructure targets. So the cybersecurity landscape is rapidly evolving with several threats, I'm sure, as you guys know, like quantum computing and emerging AI threats. Yeah, so adversaries are increasingly using sophisticated AI systems to conduct attacks at unprecedented precision and scale. And these systems can automatically identify vulnerabilities and adapt to defense measures. So but in that respect, the framework that we propose could theoretically be able to identify those attacks. Next slide. So some overall benefits and advantages. So blockchain's immutable record keeping provides unprecedented transparency into adversarial activities. Second, by analyzing blockchain records with the proposed ML algorithms, we can identify subtle threat patterns that might go unnoticed otherwise. And unlike traditional security frameworks, hopefully our implementation can continuously adapt because the training isn't very time intensive. Our framework facilitates secure information sharing between agencies, as I mentioned, with the secure sharing protocols. And particularly critical for small facilities with limited cyber security resources, our solution democratizes access to advanced security measures through the shared blockchain infrastructure, allowing the vulnerable points in our infrastructure to benefit from collective shared security. Next slide. So some implementation challenges that we have identified. First, it must be lightweight enough, and from initial testing that I've done, the model size should not be very big. Like from preliminary testing, like found that it's around like 0.2 megabytes for a sufficient model. Second, our security system has to be calibrated, like as of right now, per like water infrastructure site, because every water infrastructure site is the same. They have different like amount of stages and stuff for each facility. Third, we must balance immediate threat detection with adaptability, as I mentioned, like adapting AI systems nowadays. And finally, legacy systems are a problem because they rely on technology that's decades old and wasn't designed with modern cybersecurity in mind. Next slide. So in conclusion, our nation's critical infrastructure demands innovative protection approaches as threats grow increasingly sophisticated. The combination of blockchain technology with advanced machine learning creates a powerful security framework that significantly enhances our defensive capabilities. And I've listed some benefits here, including enhanced visibility, robust security, traceability, and so on. And perhaps more importantly, our framework enables a collaborative defense across agencies and infrastructure sectors while maintaining operational independence. And this balance of cooperation and autonomy represents the future of critical infrastructure security. That's
so. Again, just to summarize, and there were 5 students that initially gave the presentation, so some of us are reading since we're down to like 2 over the summer. But there were 28 teams that participated, and we did win for our category the best paper for this. So we're also working with Julia's help to get a crate assigned with NSA, so that at least there are different facets within the Army and others that have expressed interest in maybe actually implementing this and going forward with this. So trying to see if there's any funding that we can kind of put behind that. But we have done some preliminary work, and this concept paper is out there, so. Hi, Bob. This would be on premise, but they'd be data sharing between different agencies and others, so. Yeah, and Bob is in the Cyber Reserve, and I think we heavily utilize the Cyber Reserve with Ben Scott and others, just kind of asking in the water treatment, wastewater treatment group questions.
Let's thank Vimal and his team again.